Okay, in section 2.6, we're going to look at some of our parent function graphs and some transformation to the graphs. The reason we call them parent functions is because these, 9 graphs here are the most basic of each category that we could get, okay? They're the most basic plain line, or the most basic absolute value, or quadratic, or whatever. And then what happens is we make changes to those basic shapes, okay? So this first one, we've talked about linear equations before. Remember, f of x is like y, so y equals mx plus b, and so these are lines. Now, notice in this case, the y-intercept here is 1, so they could put a 1 in for the b, and the slope, this line goes up 1 and over 3, so the slope would be 1/3. So this particular graph here is y equals 1/3 x plus 1. But they're just trying to show you, hey, lines are in that y equals mx plus b format, okay? All right, that's a linear function, okay? Linear meaning a straight line when you graph it. A constant function just means y equals some number. So a horizontal line, remember we talked about Hoy and Vux for our horizontal lines back in an earlier unit. So this particular equation here, if you notice, or this graph, every single point on this line has a y value of 2. So y equals 2 would be the equation of it. It's still a linear function. It could still be written in that y equals mx plus b format, but y equals 2 is a good name for this line because the y value is constantly 2. That's why a constant function is a good name for it. Identity function is just a plain line, but if you notice, it's just plain old y equals x. It doesn't have any shifting up or down. It doesn't have a b value, and the slope value is 1, so it's just y equals 1x. So sometimes they call this the identity function. It's just a line. It's just another category of y equals mx plus b. Okay, y equals, these bars around the x means absolute value. So y equals absolute value of x. Notice this part over here is just a line like y equals x, but instead of traveling down over on the left-hand side, it comes back up, okay? So if you made a table of values, here's something interesting to notice about that. If I go to my calculator and I graph, to get the absolute value bars, I would hit the math button and then arrow over to the number category to the right one spot, and then option 1 is for ABS, and it will put those absolute value bars in your calculator, okay? If you have an 83, it doesn't do absolute value bars, it just says ABS and puts parentheses, but that means absolute value, okay? If I hit graph, it's going to make this picture that's on my calculator. If you want to look at the table of values, so second graph to look at the table, you'll notice whatever x value they put in, -2, -1, etc., the y value is always exactly the same but positive. In other words, if you put -2 in for x, out will come +2 for y. If you put in -1 for x, out will come +1 for y. And then, of course, if you put in 0 for x, you get 0 for y. And then on the positive x values, they always come out exactly the same. Remember that absolute value means distance from 0. So when we put -2 in for x, we're saying, hey, how far is -2 away from 0? Well, it's 2, and that value is what comes out for y, okay? So it's kind of good to remember these, 4 or 5 ordered pairs for each graph. I had a student one time that called these the Furious 5. The -2, -1, 0, 1, and 2. We would plug those values into the parent function and see what came out. And it's kind of nice to either have them memorized or where you could do it very quickly. But the absolute value function, this is what it looks like. Notice it has a vertex at the origin, okay? And then it goes up in a straight line on both sides. Okay, quadratic function. Quadratic means that there's an x squared in it. So notice this equation has an x squared. Now, if I made a table of values, and I put my Furious 5, my -2, -1, 0, 1, and 2, what I'm doing is each time I plug these numbers in for x, I see what comes out for y. Okay? Well, if I put -2 in for x, that means -2 squared. -2 times -2, which is +4. If I put in -1, -1 squared is +1. 0 squared is 0. 1 squared is 1. 2 squared is 4. Okay, I could get those in my calculator as well. I could type in y equals x squared, look at my table, and I would get those same values. Okay, notice when we graph them, -2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. It's those same ordered pairs. It makes that parabola shape. Okay? Anytime we have an equation with an x squared, it's this basic function right here, this basic picture. Now, as we put other stuff in it, like if we put a 3 in front of the x squared, or we put a minus 1 at the end, it would take this same basic parabola shape and it would move it around on the graph. It might stretch it out really tall, or it might shift it right or down or different places, but it's still going to keep that same parabola shape. Same thing with the absolute value. If I put a, minus 2 after the absolute value bars, it would still take my same basic V shape and move it. Okay, in this case, if I put a plus 2 at the end, it would move it up 2. If I put a minus 3 in there, it would just, move it sideways 3 units. Okay, so these are our parent functions because these are the basic formats. And then as you put other numbers and other symbols on there with it, it makes changes to the shape. Okay, all right, our cube function. I apologize on this picture. I do not know why that little straight line got in there. It should not be there. It should just be the curved part. Okay. In fact, you can see it better on your calculator. We make it x to the third, and we graph it. There's our shape. It does not have that straight line. I apologize if that's on your handout. It was a glitch in my printing program. All right, so we make a table of values. We can use our Furious 5 again, negative 2, negative 1, 0, 1, and 2. And I'll look at the table. I have negative 8, negative 1, 0, 1, and 8. So notice, negative 2, negative 8 would be way down here. Negative 1 is here. 0, 1, 1, and then 2, 8 would be up here. Notice how the part on the right is very similar to the parabola. It just gets a little bit taller faster. The part on the left, instead of going up like the quadratic does, it's dropping down. Now think about why that is. If we put negative 2 in for x, we'd be saying negative 2 to the third power. Negative 2 times negative 2 times negative 2 is negative 8. So when we square a negative number, it came out positive. That's why on the parabola it's going up. But when we cube a negative number, it comes out negative. That's why this left-hand side is dropping down. Okay. All right, next parent function we want to look at is the square root function. If we made a table of values, again, I apologize for that little straight line segment. I'm not sure why that's there. Square root of x. Okay, now look at my graph. It starts here at 0, 0, and it kind of curves up and to the right. Okay, if you put in 0 for x, the square root of 0 is 0. If you put in a 1 for x, the square root of 1 is 1. If you put in a 2 for x, square root of 2 is 1.4 something. That was kind of an unpleasant number. I'm going to skip that. I'm just going to go to 4. Square root of 4 would be 2. So if I go over to x is 4, y is 2. 1, 1, etc. If I went over to 9, square root of 9 is 3. So if I went way out to 9, it would finally be up here at 3. That's my curved shape that I'm seeing there. Okay. Now, why do we not have any points over on the left-hand side? Well, what would happen if I put a negative 1 in for x? What's the square root of negative 1? Oh, it's imaginary. We can't do it. So what that means is you cannot put any negative numbers in for x, because you can't take the square root of a negative number. It's imaginary, so the graph does not exist over here. Okay? We'll talk more about that domain a little bit later in the course, but just realize, hey, in this particular case, I have to put positive numbers in for x. So the graph does not exist on the left-hand side. It's only on the right. However, our next parent function, the cubed root function, remember I'm going to type my 3, then go to my math menu, and arrow down to option 5 to take the cubed root of x. And when I graph that one, notice it has the positive part over here that looks very similar to the square root part, but it also has a negative part over on the left-hand side. Both parts exist. Now think about why that is. If I make my table, cubed root of 0 is 0, cubed root of 1 is 1. If I put in an 8, the cubed root of 8 is 2. Remember? 8 is 2 times 2 times 2. We'd be looking for groups of 3. There is a group of 3 2s in 8, so a 2 would come out. So that's the positive part over here. But notice you can take cubed roots of negative numbers. Remember, -1 times -1 times -1 is still -1. So there is a group of 3 little -1s in that cubed root. So even though we can't take the square root of negatives, and the graph does not exist on the left-hand side, we can take the cubed root of negatives. So the graph does exist over on the left-hand side. Okay? So square root and cubed root function look similar, except the cubed root exists on both sides. And the cubed root is also a little stretched out, a little bit thinner, because square root of 4 was 2, whereas on the cubed root you had to go out to 8 before you could get the 2 to come out for y. Okay? And then this last one, our book calls it the reciprocal function. I don't really like that term reciprocal. I would rather call it a rational function. That's what most books that I know of call it, rational function. The word rational means fraction. So you'll notice the equation here, the f of x, or y equals, whatever you want to call that, equals 1 over x. It's a fraction, 1 over x. And again, I apologize for that little line segment being there. It shouldn't. It should just be the curvy part. So if I go into y equals and I type 1 divided by x for my graph and I graph it, there's my picture. Notice on the left-hand side, it's kind of a curved part down in the bottom left corner, quadrant 3, and in the top right quadrant we have another section. If I made a table of values, what this is saying is if I put in 1 for x, 1 over 1 is 1. So the 0.11 is on this graph. If I put in a 2, I'd have 1 over 2 for x. So notice that the 0.2, 1/2 is there. As you put larger and larger numbers for x, this graph gets closer and closer to the x-axis. What if I put in a number like 1/2? Well, 1 divided by 1/2 is 2. So if I went to 1/2 for x, I'd have to go up for 2 for y right there on my graph. And that's why as we approach the number 0 from the right-hand side, my graph is zooming up, and then on the right-hand side it's leveling off. Over on the left-hand side of the x-axis, if you put negative numbers in for x, same idea, only as you go further and further out to -2, -3, -4, your graph will be approaching 0, because 1 over -3, let's say, is -1/3. So -3, -1/3 would be about right there. If I put -1/3, well, 1 divided by 1/3 is 3. So if you went to -1/3, you'd be down here at -3. So these two parts are kind of mirror images, okay? Notice that there's one number I cannot plug in for x, and the number I can't plug in for x is 0. Because if I put in 0 for x, you're dividing by 0. Remember, we can't do that, broke division, all that. You cannot divide by 0. So that's why 0 cannot be plugged in for x, and the graph does not exist when x is 0. Okay, these are our parent functions. What we need to be aware of is that anytime you see, for instance, an x squared in an equation, you know it's going to be a parabola shape. But as they put other numbers with it, that will cause this parabola shape to move around on the graph and be a little bit different location. Every time you see a square root of x, you're going to have this half curve over here. As they put other numbers on there, like maybe square root of x plus 3 or something like that, it will take this little half curve and move it around to a different location on the graph. But the general shape is the same, okay? As we make these graphs move around, we put a +3 or a -5 or a ×4 or whatever, and these graphs move around, we call those moves transformations, okay? If you think about the Transformers movie, what happened? The little cars or robots or whatever would transform into other things. The car would transform to a robot or an airplane or whatever. So transformations on graphs means we're taking that basic shape and we're moving it around. We're changing it and making it look a little different. Okay? On the other videos for 2.6, we're going to look at some of those transformations and how to look at the equation and know what's going to happen to the graph. Okay, so in the second video for 2.6, we'll start looking at some of those changes.